So we have seen the concepts behind the deep learning algorithms, what are neural networks, how those works, what is the calculations behind it. Now we will try to work on implementation of this neural networks using Python. So before starting with any neural network, let us first try to understand what is that neural network. So we are going to talk about artificial neural network today, and we are going to implement a simple regression problem trying to predict a any regression value over here. So let us first start with understanding or a kind of recall over that artificial neural network architecture, and then we will start with the coding part over a data set. So as we can see on the screen, we have a artificial neural network in front of us. This artificial neural network comprises of input layer, hidden layer and output layer. Now let us talk about each of this layer in detail, and then we will get started with our model building or deep learning neural network building. So the first layer, that is input layer, this layer talks about adding. So we are talking about the input layer. Input layer is a layer which takes input from the data, which means it is connected to an input source of data. Input layer will process the information or take the input, and that information is passed on to the next layer, which is hidden layer. Now hidden layer comprises of multiple neurons. Each neuron is capable of doing mathematical computation over the input data. So each neuron will take input from different sources, like this is first input x1, say this is x2, this is x3 and this is x4. Now the input layer over here will take input from all the four layers and or all the four input parameters, that is x1, x2, x3 and x4, and it will do some processing. Here it will happen like some kind of processing will happen with respect to a function. It can be any activation function, that is usually we are using ReLU activation function in this hidden layers. So it will work as a ReLU activation function over here, and this ReLU activation function will process that information and develop an output which will go to the next hidden layer. Okay, so each hidden layer will have the same each neuron in that hidden layer will have the same functionality that is having for a single neuron, but the way in which it processes the information will be different. For example, input layer, the first neuron N1, let's talk about the N1 neuron, let's call this as N2. Each neuron N1, N2, N3 and so on, each neuron will do the same activity, like it will take input from the input layer and process that information and give an output. So if we are doing the same activity, why do we need multiple neurons? So the reason for having multiple neurons over here is the first neuron, when it does the processing of input data, it considers different weights for different input levels. For example, here we will have the weightage for N1 for the first variable, that is x1, x2, x3, x4. So as we can see, whenever this activation function, whenever this neuron is trying to process this information, it will also process with respect to some weight W. So how exactly this processing is happening? It is happening with respect to a activation function which is applied over the neuron. For example, here we have x1, x2, x3, x4 as the input. So the neuron N1 will apply activation function F over the input data x1, x2, x3, x4 governed by a weight W1, x1. So it is a product of weight as well as the input data. Here we have W2, x2 and so on, like all the weights, product of weights and variables. So what is happening in a single neuron, we are multiplying a certain weight which is associated with x1, x2, x3, x4 respectively. These weights are initially assigned randomly in a neural network, and that's why the first neuron will have certain weights for different parameters. The second neuron will have some other set of weights. So the weights for first neuron, say it was W1, W2, W3, weights for second neuron may be W1 dash, W2 dash, W3 dash and W4 dash. It will be different. The weights processed by N1 neuron, the weights which are used by N1 neuron is not going to be used by N2. The weights will be different in N1 and N2. So that is why we can see different level of processing happening in each neuron, which means even if the neuron, each neuron is taking some input x1, x2, x3, x4 and processing it with the help of same activation function, but the weights are different in each neuron, which means the processing is different in each neuron. I'll give you a practical example. For example, we are developing a neural network for predicting whether a particular animal is a cat or a dog or something. So x1, x2, x3 and x4 are four different parameters. Say x1 is the shape of that animal, x2 is number of eyes, x3 number of tails, and x4 the size of that animal. So now if we talk about this all four parameters, we can see that x1 which basically is the shape of that animal is relevant to identify whether it is a dog or cat. x2, x3 basically tells us number of eyes and number of tails. So dogs and cats have same number of eyes and same number of tails. So we do not need these two parameters, which means our neuron, whichever neuron we are talking about, it should process, like say first neuron is giving more importance for x1, x2 and x3, but ideally x2, x3 are not so important, x4 and x1 are important. So each neuron will analyze the data with respect to weights which are associated, and a particular neuron which correctly identifies the differences between whether a particular animal is a cat or dog, that particular neuron will have higher weightages with respect to the input data, that is x1, x2, x3, x4. So say N4 is the neuron which correctly diagnoses whether a particular animal is going to be a cat or dog, because N4 ideally gives higher weightage to the shape of the animal and the size of the animal, because shape and size will basically tell us like, yeah, particular animal is going to be dog or cat, but the number of eyes and number of tails are going to be same for both the animals. So it is not going to help us out much in diagnosing whether it is a cat or dog. So ideally, considering this situation, each neuron judges based on different weights which is assigned. So N4 has higher, say N4 is giving correct diagnosis, which means N4 is having higher weightage to the x4 parameter and x1 parameter. It is giving the least weightage to x2 and x3, and that is why we are correctly getting N4 the output from the N4. And similarly it goes, the output of N4 is kind of passed on to the next neuron layer or the next hidden layer. Now let's talk about what is happening in the next hidden layer, H2. So say this is our hidden layer H1 and this is my hidden layer H2. H2 is doing what? H2 kind of summarizes the processing output of the first hidden layer. So whatever is the output of the first hidden layer neuron, that output is passed on to the next hidden layer neuron. So this is kind of an neural mechanism which we have in human body. We are having the similar kind of mechanism over here. Why? Because we are trying to distinguish between a particular animal being cat or dog based on certain parameters, and maybe the first layer of the output of the first hidden layer, we want to strengthen that output further, we want to dive deeper into the outputs of each of the neuron. That is why a second neuron will help us do that. What this neuron will do is it will take information from the first two, three kind of neurons, and like all the neurons, and it will do some processing. Now this is our hidden state 2, so I'll call it as n1 dash, uh, n1 dash, and it will do the same for processing as we are doing in a single neuron. So whatever processing is happening in this neural network 1 or neuron 1, the similar kind of processing may be happening in the second neuron which is there in the hidden state 2. And similarly all the neurons, and it also works in the same way. It initially has the same some random neurons or random weightages, and according to the outputs that it is receiving, it will generate the output for the next layer. And whatever is the output for each neuron in this hidden layer 2, it is kind of helping us to give us some kind of output in the output layer. So now let us talk about output layer. Output layer is the layer where we get the output. Here we will basically get the probability of a particular animal being in a particular category. For example, this first part is the probability of being a cat, second part is probability of being a dog, third probability of being a sparrow, or probability of being an elephant or something. So any kind of whichever, like after doing all the processing, whichever category, whichever output layer has the highest probability, that is considered as a as our neuron, or that is considered as our output. So this is basically happening for classification. If we have classification, we will have 4 classes, but if in case we have regression, we will have only one output element, which means here we will not have 4, we will have only one, which means all the hidden layer 2 output is going to give us a number over here, and that number will be similar to the output of that input data. So this is how the architecture of ANN is. In ANN, we take input in the input layer, we process the information in the hidden layers, and we get the output in the output layers. While we are doing regression, in regression regression we will have only one neuron over here, not 2. If we are doing classification, we have more than one neurons in the output layer. Now let us start with our program. So we have seen what is the architecture or of this ANN, artificial neural network. It is a simple architecture: input layer, hidden layer, output layer. In hidden layer we have neurons. Neurons will do the processing, and then we will get the output. Now we will talk about the data, and we will import the data. First we will import the library, that is pandas as PD. We will then import numpys as np, and we will import matplotlib.pyplot as plt. Now let's talk about what are these libraries. Pandas help us to get the data from an external resource. We can do some level of analysis, some level of data cleaning using pandas. NumPy is used to store the data in a form of NumPy array. Why we are using NumPy array? Because if we have a vector of data, so NumPy array is the best possible way to store it, because it does faster retrieval of information, faster processing of information. Calculations are faster compared to traditional way of storing the data. And then we are also using matplotlib.pyplot as PLT. So pyplot is a sub library within matplotlib, which is helping us to create charts, graphs with respect to the data. Now we will import the data. So we have a data over here. We are reading this data. The data is stored in my current working directory. So my current directory is downloads folder, and that is where my data is also placed. So this is our data.csv, and we will read the data df by using pd.read_csv. Read_csv is a function in pandas to read the data which is in CSV format. Then once we have a look at the data, we can see we have age column, we have education level, we have occupation, number of dependents, location, work experience, marital status, employment status, household size, ownership status. Then we have type of housing, we have gender, primary mode of transportation, and then we have income. Okay, so we have all these columns with us in our data. Now we will yeah, we will try to understand the data in a much better way. So we are going to do a regression problem. So practically, don't we are not going by a logical approach here. We are just going to use this all input variables and develop an output, regression output as a numerical output. Okay. So right now we do not have to go with the logical sense of this problem statement. We will go directly with the implementation part, how we can implement a regression uh, operation using artificial neural network. Then here we have df.info, which will basically give us information of each and every column in our data. So we have age, and age column has 10,000 observation which are non-null, and it is of integer type. Similarly, education level, which is again object data type. Occupation, which is again object data type. Number of dependents, it is an integer data type. uh, Location will have object data type. Work experience will have integer. Marital status object. Employment status object. Household size, it is integer 64. Home ownership status, it is object data type. Type of housing is again object. Gender is an object, and primary mode of transportation is again object, and income is also integer data type. Now what is this data all about? This data is telling us that whether the type of information inside that column is integer type, it is numeric, or object type, whether it is an alphabetical string value. So if it is an alphabetical string value, it is telling us that it is an object data type. So we can also see the size of the data type, data here, which is 1.1 plus MB, and we do not see any missing values here in our data. So let us move to the processing of this data. So initially we need to do a little bit of processing of this data. So for that, we will separate out data into two parts, that is categorical columns and numerical columns. For that, we will create two lists. One list is cat and another list is num, and I am doing this without having a logical flow. As I told you, we are here to learn how to implement a regression over a certain data set, whether it is a regression or classification, whatever is the data set, how to utilize it for ANN, like how we can implement an artificial neural network over an data set. So that is the purpose. So right now we are not going with a very logical data cleaning approach, but yeah, to some extent we will try to do justice to this data set and try to retrieve practical possible information. So categorical is a list and num is a list, and what we are doing is we are iterating over each and every columns in this data set. Okay, so df is our data set. So for I in df dot columns, which means I basically represents each and every column, and we are checking if the type of the column is O basically tells us object data type. So if the type of the column is O, it will be added to the categorical list. Otherwise, it will be added to the numerical list. Right now, we have only two type of data, that is integer and object. So we will use this if else condition. If in case we have float 64 or something else, so in that case we or date and time. So in that case we can have multiple if and else kind of operations over here. So this loop, this code will basically separate columns into two parts. Like it will just give me a list of separate columns. First list is cat, in which we will have only the categorical information. Second list is num, in which we will have only the numerical information. Then we will move on to creating charts using this data. So we will create different types of charts. So if we are having a categorical information, so what kind of charts we can do? We can ideally develop a bar, horizontal bar chart. So we are iterating over each and every column in cat. Okay, and what we are doing is we are creating value counts for each and every column. So for I in cat basically represents each and every categorical column. df of I means df and that categorical column. That categorical column we will calculate the value counts, which will tell me how many what is the count of each category in that column, and we are developing bar H. So bar H is going to help us to develop a horizontal bar chart, and horizontal bar chart on y axis we will have indexes, which is nothing but names of the categories, and on x axis we will have the width as the values of the value count, which means y axis we will have indexes or the name of the category, and on width of that each bar will be decided based on what is the proportion or what is the size of that, what is the count of that value or the category. And we will also use plt.title to show the title, and then plt.show to end the visual, each visual. So here we can see different columns. So first categorical column we can see, that is education level. In this education level column we can have different education levels, that is doctorate, masters, high school, bachelors, and kind of this data is arranged. We have higher number of bachelors in our data. Then we can see occupation. In occupation we have different occupation categories, kind of balanced. Then we have location. We can see that most of the people are from the urban background, very few are from rural and then suburban. Then marital status, we can see in marital status also most of the people are married than single. Then we have employment status, we can see full-time, part-time, self-employed. We are trying to visualize each and every categorical column, trying to understand which column has what is the distribution of each category in those columns, and we can clearly see each and every data is quite distributed. We do not see a perfect imbalance in the data as of now. So that is our categorical data we have visualized. Now we will move on to the visualization of our numerical column. So we have also we can also develop the charts for numerical data like this. So for I in num we will apply a for loop on the numerical data and extract each and every numerical column. And we are going to develop two charts for numerical data, that is ideally we have a box plot and second one is histogram. So first chart will be an histogram, second one will be a box plot. We can interchange the positions. We are using subplots approach of PLT or matplotlib. In matplotlib subplots we divide the data into two categories, like here we have 1 and 2. So what this basically tells us, so in each subplot I want two charts, which means one row will have two charts. That's what this 1 and 2 basically indicates. This is the size of each chart, and on the first AX0, so this is my AX0, on this I want histogram, and this is my AX1 on which I will be creating a box plot. And plt.super title, this is a super title which will be imposed over each of the two charts, like this is a combination of two charts. So super title is a super title of these two charts, which is nothing but the name of that column, and plt.show will show that visual, which means if I'm running a for loop I do not have to, like, it will not overlap over each other. So that is why plt.show will help us. So let's see what are the charts that we have developed using this for loop. So the first column, that is age, and we can see a distribution of age which starts from somewhere close to 18 to 20, and the age distribution is still 70. There are higher people between the young age group and the old age group, and it is quite symmetric distribution, as we can see over this box plot as well. So no outliers present. Then we will move on to this number of dependents column. So number of dependents column also shows a significant level of data distribution on the histogram as well as this box plot, and it is also quite symmetric in nature. Similarly, work experience data is also symmetric in nature. Household size is also symmetric in nature. These are categorical kind of information, and doesn't represent a continuous flow of data. That's why it will always be continuous, or it will always be symmetric. Here we have a column that is income, which is not at all correctly showing the symmetry, or this data is right skewed, because we can see there are a lot of outliers here. Outliers basically indicates there are people who are earning more here, and very less proportion of data is there which is outlier, and there is a presence of outlier. So let us try to analyze the data. So we have seen the data, kind of understood where the problem lies, and now we will start with understanding the data correctly. So we have these all columns, we'll keep it open, and we will start with analyzing the data. We will use the label encoder and one-hot encoder to properly encode all the categorical data. So we'll start with education level first, and we are doing encoding. We are not using label encoder or one-hot encoder directly. We are using dot to replace as an alternative to one label encoder. And wherever we see high school, bachelor's, master's, doctorate, we are giving manually our own hierarchical data setup, that is high school is 0, 1 is bachelor's, 2 is master's, and doctorate is 3. And we are using replace function in the education on the education level. So we are replacing so in the education level, wherever we see high school, bachelor's, master's, doctorate, we will replace it by numbers. Now why we are converting data into numbers? Because the machine learning algorithm or deep learning algorithm will not understand what is high school, what is bachelor's, what is master's. So we have to encode it into a proper number so as to make the machine understand, yeah, this particular number represents this particular information. So we can do the de-encoding part or decoding part later on, but this is how we are going to create the data or encode the data. Then we'll do it for education level. We see the data. Now we'll do it for occupation, and occupation is also quite balanced, and we are using one-hot encoder here. The reason of using one-hot encoding is, so what is a one-hot encoding? One-hot encoding, well, first of all, convert the data. So say I have only 3 categories: A, B, A, and C. In my data I have only these all data, which means there are uniquely 3 categories. So when I do one-hot encoding, it will convert the data into columns. This one column will be converted into 3 columns because I have 3 unique information, A, B, and C. And wherever I see A, it will put 1, and rest of the value it will put 0. So wherever I see B, it will convert it as 1, and rest of the 0. Similarly here, and when I say C, it will put 1 here, and it will put rest of the data as 0. So what is one-hot encoding? One-hot encoding will convert the data into a numerical version. It will convert the data into a version where the categorical data is converted into numerical, and each category will now be becoming a new column. And when we are doing one-hot encoding, we convert the data accordingly. So for that we use this one-hot encoder function, and we are keeping sparse output as false because we do not want a sparse matrix to be created for each column or each level of data. Then we have we are creating one-hot encoding array. We want that array because when we apply this one-hot encoder over column, it will create an array. So we are creating a one-hot encoder of occupation column. We will use fit transform over it, and once we do the fit transform, we apply it over occupation column. Make sure that we are using double square brackets. Double square brackets basically helps us understand that this is a data frame that we are trying to encode. And then once we do it, we get an array which is one-hot encoded, and of that array I will create a data frame. So I will create a data frame called occube using pd.data frame, and the input data will be occuped array. And columns, we are using OHE computation dot occupation dot categories, which means this one-hot encoder which we are using, from there we are getting the column names. Now what is this column names? These column names are nothing but A, B, and C for our. If the data has A, B, C as categories, these categories will uniquely become as the columns for that array. So the array, say if array has A as the first column, B as the second column, C as the third column, numerically presented, so is going to be represented by OHE occupation dot category. So it will sequentially give us according to the generation of the array. The column names we will get A, B, C accordingly. So whatever is the occupation, say healthcare become first column, technology will become second, finance, others, and education. Once we do an one hot encoding operation, what we will do is we will treat the data, or we will script the first column, which means we are removing the healthcare column and we are keeping rest other column. We are not, like when we create this data frame, occup data frame will have multiple data. So I'll show you what is this occup right now. So this occup column or data frame, okay, I need to run it all. So occup column is having education, finance, healthcare, others, and technology, all these columns. And what we have done, we have healthcare, technology, finance, others, and education. These are how many columns? 1, 2, 3, 4, 5. And here also we have 5 columns. Now once we apply, see, when we are using these columns, it will show us perfect correlation among itself, which means that if education is 1, rest other is going to be 0. Similarly, if tech finance is 1, rest other is going to be 0. So here we see that if we know that which one is 1, then we are able to easily able to understand or recognize others are going to be 0, which means these are interdependent or correlated. If we know any one column, if it is 1, rest other columns are automatically understood that it is 0. So this shows a clear correlation among itself. So that is why what we will do, we will try to remove this collinearity or correlation among this data, or multicollinearity. This is a multicollinearity problem where the data is actually connected or the data is actually connected or actually correlated with each other. So we need to remove this collinearity, because that will not help us in the that will not help us in model building, because the primary assumption of building a model or machine learning or data science or any model tells us that the data should not be correlated among itself. So that is why we need to remove one column, and that is why we are using this ilog method. Ilog method will remove one column, and say we are removing first column, we can remove any column. So but we are here removing only the first column, so we remove the first column using ilog, and that's how we do it for others. So we will check which all categorical columns are there. Education level is done, then we will go for occupation is also done, then we will go for location. So location column has 3 columns, 3 categories: urban, suburban, and rural. Now for urban, suburban, and rural, we will try to replace it, and we'll try to give us it a label encoding. So urban we are giving 1, 2, suburban we are giving 1, and rural we will give as 0. So here we are doing label encoding, and we'll move forward. And then we have this location column. Location column again, we will do the location column has automatically converted to 10, which was earlier urban, suburban, and rural. Then we will do it for marital status. Marital status, we can see married, single, divorce. Here also we have the data, but we cannot see any hierarchy between married and single and divorce. So for that we have to do one hot encoding for that information. And here we are doing the same way, one hot encoding, where we first create a one hot encoding one hot encoder for object, and this one hot encoder object will fit transform over the marital status data, and we will use pd.data frame to create this one hot encoder. So we will use this array which is generated, and columns we are going to use the columns one hot encoding ms dot categories. So we are going to use the same one hot encoding method that we have used recently, and we have successfully converted a marital status column as well. Then we have again this categorical columns. Now we will try to understand marital status done. Then we will do it for employee status. Employee status again full-time, part-time and self-employed. It cannot be hierarchically recognized. That for label encoding is not possible. So label encoding we cannot do it. So we will do one hot encoding again for this data, and we are removing the full-time. We are keeping part-time and self-employed. So then we will use home ownership status. Home ownership status basically has only two categories, that is own and rent. So we can simply do label encoding. We can use replace method. We will set own as 1 and rent as 0. You can do vice versa, it doesn't matter. Only thing is we have to put a label number for that particular data. Home ownership status is also completed. Now we will do it for type of housing. There are three type of housing, that is single family home, apartment and townhouse. And here also we need to do one hot encoding, and we will do one hot encoding and convert the data. We are removing one column over there, and then we use it for gender. Gender has only two categories, that's why we can simply do label encoding, converting male as 1 and female as 0, because machine will not understand what is male, what is female. It will understand only 1 and 0. Then primary mode of transportation. Primary mode of transportation we have 1, 2, 3 and 4. Therefore and these are not hierarchical related, which means public transport is not going to be superior than car, or car cannot be superior than public transport. The likeliness or occurrence of these data are not interconnected or hierarchical in nature. That's why we have to do one hot encoding here as well, and we do one hot encoding, that is car, public transit and walking we are keeping, and we are just removing this one category, that is biking or something. We are just removing it. Now once we do that, what we will do, we will drop all these columns which have been encoded successfully. So we will drop it, all the columns: primary mode of transport, type of housing, employee status, marital status, occupation and income, because these are one hot encoded data. This data has been one hot encoded and created into a new column. So a new data frame. So primary mode of transportation is a new data frame now. Type of housing, which was earlier one column, is a new data frame called as TH. Employee status, which was one column, which was transformed into multiple columns, that is a new data frame. MS, which was earlier a new one column, it is transformed into a new data frame MS. And occupation, which is a new column, which is transformed into occupation. So likewise all the columns needs to be transformed, and we have transformed this. We will add the data which was there, okay, wherever all these columns were there. Similarly in the same order we are going to add the other columns, the same columns data frame. So for example, right now in our X we have age, education level, number of dependents, location, work experience, household size, ownership and gender. We have successfully done the encoding part, label encoding part for these all columns which were categorical, and numerical column we do not have to do any change. Rest other columns we are doing change, but we will concatenate the existing X which had these all columns with the data frames of these columns which are removed. So how we are doing it? Say for example, I have age, education, all these columns till gender. Now public transport we are adding, which is car, public and all. The single family home, type of residence we are adding, as well as employee status, marital status, occupation, all this category of columns we are adding, okay. So once we do it, we have an array which is not losing any information except the one categorical column from each of the one hot encoded columns. Why we are doing it? Because we just want to remove the multicollinearity effect over here. So this is our set of columns, and then we will use y is equal to df income. We are creating a new column which is y or array. which will hold income column. So here we are predicting income of a people, of a person, based on certain inputs which are here, like age, education level, and all other inputs. Based on these inputs, we are converting, or we are trying to find out income of an individual. So our X is going to be all these columns, and our Y is going to be the income columns. Then we will install TensorFlow. If you already have TensorFlow, no need to install. Otherwise, you have to use this command pip install TensorFlow. It will install the latest version of TensorFlow. Then we will import TensorFlow, which is just now installed. We will import TensorFlow as TF. We will then import Kera's sequential model. Why we are using sequential model? Sequential model will allow me to stack one over the other multiple hidden layers and layers. So we are using sequential model. Then we will use dense. Dense is a layer. Now what is this dense? We will discuss at the time of implementation. Then we are using train test split to split the data into training and testing, and then we are also using standard scaler. So what we will do, we will first split the data into training and testing. So we have already done this in machine learning. We'll try to understand what happens here. So our data X and Y, which is our input and output, we split the X and Y into two further parts, that is two parts, that one part will be a training part, another part will be testing part. So X train and X test is a division of X, and Y train and Y test is a division of Y. X train has 80% of data, because the test size we are keeping here is 0.2, which means testing data will have 0.2% of data, which means 20% data is testing and 80% data is training. Why we are putting 80 and 20 as a split? Because 80 and 20 is the right proportion to train and test a model, so as to make the model understand the hidden features of the data and also validate the model. So that's why we are using training and testing. So X train we are keeping and X test we are keeping, then we have Y train and Y test. So whatever is the corresponding X value, for that value the Y value will be selected in the splitting part, and the training and testing of data is shuffled and it is then splitted. So we are using a random state here, because train test split will always split the data into randomly. So randomly we are getting a pair of X and Y into X train, Y train, X test, Y test, and random state we are fixing as 0, because we do not want to keep the data changing all the time when we are running it. After that, we'll call the standard scaler. Now we have imported the data. The data that we have is in different order. If you talk about X, we can see age is 5669, but education level is 210, 210. Number of dependents is 50, 123, and so like that. And location is 122, 212, like that. So we can see each of the data is not on a single scale, which means this is in 2 digits, this is in 1 digit. Somewhere we can see data which is in again in 2 digit or 1 digit and like that. So we want to keep a uniformity across all the data. Why we do it? Because that helps us in doing faster processing of data. And as we are doing a deep learning model building, so deep learning always is a computationally expensive. That's why it is better to scale the data. So it is better to scale the input data, that is X train and Y train. So we scale the data using standard scaler. If we transform the X train, we will transform the X test based on the training fitting which we have done on the training data. Then we are using model as sequential. This is our model. So sequential is our model. Sequential enables me to put all layers one over the other. Then we will have a look at the shape of the X train. So X train has a shape of 21. So why we are doing this, I will tell you, because we want to fix a size of the input data. Before going into model building, so we have created a model is equal to sequential, which is an empty model, and which will have multiple layers over it. So right now it doesn't have any layer. So before going into layer building, let us understand what is this, what is the concept of activation function. So we have discussed recently what is an activation function. So activation function is the processing. So say this is our neuron and it is taking some input x1, x2, x3, x4 as we discussed, and there are certain weights associated, weights 1, weights 2, weights 3 and weight 4, and there are certain values to these weights. Now what happens in the activation function? Activation function takes input data and processes the data based on the activation function that we have decided. So whatever is the input value here, our activation function, whatever activation function, according to that the value is processed and a signal or a value is generated as an output. So if it is a step activation function, so it will set the data into two stages, that is 0 or 1, which means whatever is the value, it will convert that value into 0 and 1. Similarly, sigmoid activation function is a binary activation function which will give me probability of values. Okay, so it will give me two set of probability values. Basically higher values basically indicates that that is going to be one category, lower probability values indicates that it is a 0 category. So that is our sigmoid activation function. Then we have softmax activation function. Softmax activation function basically converts, takes all the input data and converts it into the n number of categories. If we are having 3 categories, so softmax will convert it into 3. So 3 probabilities it will give, Thailand, Jamaica, Dubai, say for example. So it will give probabilities of being Thailand, being Jamaica or being Dubai based on this input data. Similarly, we have tanh activation function. Tanh activation function gives me data as negative or positive. It is kind of a linear set of activation function. It is giving us value between -1 to +1. Then we have ReLU. ReLU activation function gives the data as 0 or positive, which means whatever, after processing this data, after doing some computation, whatever is the value, it will convert it into, if it is negative, it will convert it to 0 or it will convert it to positive. So if it is negative, it will convert to 0, or if it is positive, it will keep it as it is. So ReLU activation function converts the data as 0 or positive. So these are our activation function. Now if we have this clear understanding of this activation function, we will slowly implement this activation function, and slowly you will be able to understand what are the uses where we can use this activation function. Okay, so let's move forward. So initially we have created a model sequential model which is empty and it doesn't have anything over it. So what we will do, we will first add a dense layer over it. So we are adding a dense layer of 128 neurons. Now this is a dense layer, and what is a dense layer? So when we talked about our neural network, so dense means each neuron in this first layer is connected to each neuron in this next layer. Okay, so dense activation function basically tells us that dense layer is all about connecting all the neurons to all the neurons of the next layer. Now this is our input layer, and that is why we need to specify input dimension. So input dimension is equal to the number of columns that we have in our data. So in our data we have columns as 21. We have 21 columns. That is why we are going to use the extend.shape 1, which means I am taking 21 input from our input data, and then activation we are keeping it as ReLU, which means in the first layer the activation function is going to be ReLU. Now in the second layer we are keeping ReLU activation function. Why we are using ReLU? ReLU is used to break the linearity among the data. ReLU brings non-linearity in the data. It removes the dependence of a data. That is why ReLU activation function is very much helpful. Then we are reducing the neuron size after every layer. So here we had 128 neurons. In this layer we have 128. Here we have 64, then we have 32, and in the output layer we are having only 1. So in output layer we are keeping one output, which means we are keeping only one neuron as an output. That's what I'm saying, that in the output layer, if it is regression problem, we will keep one neuron only. That neuron, basically whatever is the output of that neuron, that basically is our output or y value. So we have constructed this model. After that we will use compile. So when we use compile, the optimizer is going to be Adam, and optimizer, what is optimizer? Let's discuss this. Optimizer is the method of recorrecting weights. So in our neural network, if we talked about this neural network. So in neural network we are propagating in forward direction like this, and we are generating some output in the forward direction. If we are moving in the forward direction, a output is generated. Say in my case I have only one neuron, so we are generating output for this neuron. So this output is compared against the actual value of the output, which means for this set of input data, what is the output data. So when we talk about a neural network, we have something called as a forward propagation, and then we have backward propagation. So what is backward propagation? In backward propagation, we see whatever is the output generated by this neural network, and we compare it output with the actual data value. And this is what we are going to do here in the backward propagation. We see what is the difference between the actual and the actual as well as the predicted value, or the value generated by the neural network. And the purpose of this neural network training is to minimize the gap between this actual and the predicted value, and that's what we do in the backward propagation with the help of gradient descent and different optimizer algorithm. And that's what we are going to do. We have discussed already all these optimizers in the theory part, and we can see we are using this optimizer, which is Adam optimizer here, which is the best optimizer. And Adam optimizer helps us to optimize in a way that it converges to the lowest possible error with high speed and effectively, and that is why Adam is used. It is very effective optimizer. We are using loss calculation with respect to mean squared error, and metrics we are using is the mean absolute error, which means we are trying to reduce the loss, which is mean squared error, and the performance we will be governing with respect to mean absolute error, which we want to reduce. Then we compile the model. Once the model is compiled, now we will fit the model with the data. So the data that we are going to fit here is the X-train and Y-train values. We are putting epochs as 500, which means we are trying to build up 500 times of training, which means what? In each training we are using a batch size of 32, and validation set split we are going to use as 0.2. Now we take data set in an epoch, and we train the model on that data set, and whatever is the error generated, we try to reduce the error by changing the weights of that neural network. So in the next epoch we will change the weight, and we will change the weight in a way Adam works. Okay, Adam is an optimizer, basically a gradient descent algorithm. So it will try to reduce the loss, which is MSE. So weights will be changed with respect to reducing the loss, and every iteration this operation happens. So in the first iteration training happens, and in the second iteration the weight adjustment and retraining of the model with respect to the new changed weight will happen. So we can see that initially the loss is very high for validation data. Mean absolute error is also very high, 77.3352. And as we move forward in the next iteration, yeah, again it is very high and the loss is also high, but in the third epoch the mean absolute error goes down from 77 to 74. Similarly, it goes down further up in the next iteration, then again goes down, and as we go forward in each and every epoch we can see the mean absolute error is going down and down and down. So as we move further with the final, if we talk about the last epoch or last set of data where we are training it, we can see a comparatively very low mean absolute error. So earlier we started with 77, uh, 77 like 7,70,000 was the error that we saw in the initial in the first part, but 7 lakh, just let me confirm the number, it is 7,73,000 was the initial starting error or mean absolute error, and at the end let's see what is the mean absolute error, which is, it is going to be somewhere 1,03,000. So it is getting reduced by 6,000. If you increase further the epoch, it may also get reduced. See what happens in a gradient descent is our algorithm. So if we talk about the weights and if we talk about error, so error keeps on increasing, reducing at a point, and again it goes back up. So you can see somewhere it is up and somewhere it is low. So our objective is to find out a spot where the errors are least or mean absolute error is least. So here we have least error compared to this, okay, and if we see the convergence, so our errors or our gradient descent algorithm goes in this direction where error is least at this point, and the way we are fixing the learning rate, it will automatically converge. So it keeps on happening and we are actually moving forward. So if we are increasing now further the epochs, it is not necessary we will go to where lowest value of error, it is the error, the lowest value of error is fixed, like below this it cannot be going lower further. So that is why here we have to stop, and we see that at the epoch number 498 we have a considerable lower value of error, and this is something which we can store it at the later point for building the model. So right now if we talk about this entire scenario, we have kind of optimized. We were at 7,73,000 and right now we are at 1,32,3,000, which is the lowest error. Now once that is done, we will evaluate the performance of the model. So for that we need to find out the loss and mean absolute error by using model.evaluate, and we will evaluate over the testing data, and we see on the testing data we are getting an error of 851, which is too high. We'll try to test this data and how the errors are going with respect to training and validation. So for that we will try to reduce, or we will try to plot the data using the plot function, and we are going to plot the actual model loss with validation loss at each step. And what we are going to do is we are going to have the epochs on the x-axis and loss on the y-axis. So we can see that the blue colored line basically represents the loss of the overall model, while the orange color line basically represents the loss at that particular validation data set. So we can see a considerable, the loss over the data loss over the actual model is very less compared to the validation loss at the validation is very high. So this is how the model is developed. Now if we want to fine tune the model, we can change the parameters, we can change the epochs, and we can increase the number of layers in a model. For example, here we have used, so here we have used 1, 2, 3, 4. So there are 3 hidden layers. We can increase the number of hidden layers and the number of neurons, and based on that it will help us out in getting more accuracy towards the model. Now one thing we have to keep in mind, if we increase the number of layers, so the model will become heavy and it will take time to process the information and develop results or give some output. So based on that we have to decide like what is the processing power that we are having with our computer and all, or whatever application we are using. If we are using an application, how much of computational speed we can afford to provide to that model. So based on that we need to decide what what kind of model and how much dense it should be. So at the end we can develop predicted values, and we can predict the data using the predicted values, and we can see y-test predicted values we have developed. We can compare the predicted value with the actual value and try to find out how much is the performance. If it is good enough, we can definitely go with the model. So right now we are using uh, a very common data which is not at all aligned with linearity, and it is not a logical data set, to be honest. So we are just using randomly one data set. We are considering some parameters as input, and we are considering one parameter as output. So the objective of doing this is so that you can you can work on any models without any so that you can develop any models if you have such kind of data set. So this entire code helps you out with developing model, and with any kind of data set if you are doing it for regression purpose. So we have seen how we perform regression. So we are now going to perform classification over our regression over our model or over a data set using ANN model. We are using ANN here for classification purpose. So as we can see in this data set, here we have this model. We are using ANN. The architecture will be same. This is our input layer. These are hidden layers. This is output layer. These circular bodies basically represent neurons, and there will be a different set of activation function. We have already seen the activation function and description in the previous ANN regression class. So we will skip this part of introduction to this ANN. Definitely you can refer to it for reference and understand better. Now we will move on to the data set, the actual data set. First we will import pandas as PD, and then we'll import numpy as NP. We'll use matplotlib.pyplot as PLT. These are the general dependencies or libraries which will help us to process the data and organize it in a very structured way. We have already discussed this. We are reading the data set and we'll try to understand the data set. We have user ID as a column, we have device model, operating system, app usage, and all different form of columns are there. Screen on time, we have battery drain, we have number of apps installed, we have data usage in megabytes per day, and age, gender, and behavioral class. This behavioral class can be anything, like it can be these classes basically represent a severity of usage of phones or devices of an individual. So these are individual. This single row represent an individual, which phone he is using, and what is the usage statistics, and in which category this particular person lies into. So now we will try to understand this data better with the help of info function, and this info function will give me the data and its statistics, how the data is actually distributed. It is having 700 non-null values, 700 non-null values in each of the column, and there is no missing value actually, and we can see some integer values, float values, object, and all different types of data is here. Then what we will do is we will start analyzing data one by one. So the first thing that we will do is gender column. We will see the gender column, the count is quite symmetric, it is balanced, and we are not doing visualization here. We will directly be doing the data cleaning part, and we apply label encoder over a column that is device model, because it is a categorical column. Device model, if we talk about this column, we are going to apply label encoding. Why I am applying it is just to convert the number, just to convert the data into numeric part. Here my idea is not to get a highly accurate data model or machine deep learning model. Here my objective is to show you how the implementation works. So I'm not bothered about what kind of data is there inside this column. I'm just going to implement it straight away. So I will implement label encoding. By logic it should not be there, label encoding should not be there, but just to ease out the process and speed up this explanation, that is why I'm just using using label encoder here, which is also fine, which will help you to understand better about the data. So each devices will be encoding with respect to the model or device it is having. Then we have label encoding done over the operating system. Here we can do label encoding. There are different operating system. We can see Android, Google and all. So we are applying label encoding over it. Actually by logic we have to go and we have to convert this as one hot encoding, which we are not doing for the sake of time convenience. So ideally you should go for one hot encoding for these two columns. Now we'll move forward with the third column, that is operating system. We have already converted it as label encoding, and after operating system we will use gender, on which we are again using label encoding. Gender has only two categories, so it is fine with label encoding over gender column. Now we will drop certain columns, that is user ID, behavior class and operating system for X. So in X we will not have user ID, behavior class and operating system. We will convert it into we will remove it, and on the X is our independent data or input data. So X will not have all these columns, the rest other columns will be there, and Y will have only one column, that is user behavior class. So Y will have user behavior class as only column. And what we are going to do is we are subtracting Y with one value, because when we if you see this user behavior class, user behavior class has values 1 to 4 as values. There are 4 categories in user behavior class, which is 1 to 4. So as it has 1 to 4, and we are developing a deep learning model over it, and when the deep learning model starts working and we use the deep learning model, and when we develop an algorithm and it tries to develop some relationship, so 1 to 4 are not the number it is going to consider. It is always going to start with 0. So it wants 0 to 4 or 0 to 3. So here we are using 1 to 4. So 1, basically what we will do is we will subtract each value with 1. So 1 will become 0, 2 will become 1, 3 will become 2 and 4 will become 3. Like that we are going to do. And there are 5 unique values in Y, so which means there is values from 0 to 4 here. And then we will apply standard scalar over our X data, and when we apply standard scalar over X data, entire data will get reduced to a lower version. And once the data is getting reduced to a lower version or a version which can be suitable for computation purpose, then we will split the data into training and testing part. It is fine if you do it after or before. If you are doing it before, so better you do it for entire X. If you are doing it after, then you have to do it for training and testing, as we have done in the regression class. So both the methods are fine. So you can see the regression ANN regression class or the tutorial, where you will see the alternate approach of doing training, testing, split, or doing the standard scalar part. These two process we can do in alternate methods. Now we are splitting the data in the same proportionate that we have used recently. So 0.2 is the testing size, and training size is going to be 80% of the entire data. We had 700 data points, so it is going to get splitted accordingly. Now here we will again import the model, that is sequential, and then we are using layers such as dense and dropout. Now this dense and dropout, we have already discussed about the dense layer. We will discuss about the dropout layer, what exactly it is going to do in our model. And these are all activation functions which we have already discussed in the previous class. So right now I am going to skip it, and we will move ahead with the model building. So here we have a sequential model, which is an empty model basically, which allows us to stack up layers one over the other. And the first layer is the input layer, which is a dense layer with units or neurons as 128. And here we have activation function as ReLU. Always ReLU is going to be activation function for the input as well as hidden states. And input dimension or the data that we are getting is going to be in the shape of xtrain1 dot shape1. So xtrain1 dot shape1 will give me the input data, or the columns, number of columns in the input data. And then we are going to apply the dense layer. So dense layer will get connected. Say if I have this 2 neurons and here I have 3 neurons. So when I am applying dense layer, each neuron is connected to each other data point here. So that is our dense approach. Now we will move on to the dropout layer. So next dropout layer has 16 say output or 16 neurons. So say I have a next layer which again has say 3 neurons. Okay, so between these two neurons I am putting a dropout of 0.3, which means if I am connecting this with this, so I am not connecting, I am just connecting with a proportionate of 30%. I am going to drop 30% of data or 30% of linkages to the neuron, which means not each and every neuron is connected to the every neuron. There will be a drop. Say this is connected, this neuron is connected to all 3, but this neuron is connected to only 2. Sometimes this neuron is only connected to the first and the last. So such kind of dropout will happen between these two layers. So dropout layer will not connect each and every layer with other layer. It is going to connect partially based on the dropout proportion that you are going to mention. Now when we are doing this dropout, so it will always drop out the data or data linkages or this neuron connections. So what is going to happen when we are doing dropout? So what happens when we are using dense layers? So in a dense layer, the data is the machine learning or the deep learning model is doing a lot of learning. It is trying to learn each and every feature in detail. When we are doing such kind of things, so the model becomes very active and it becomes very data dependent, which means it is very much dependent on the input or the training data on which it is learning. It is very much reliable, but it is not reliable with the new set of data, which means if I have anything new to be if I have any new data which I am getting the model exposed to, so model will not be able to work well on the new data. It will do overfitting, which means it will work on the training data well, it will give good accuracy on the training data, but on the testing data it is not going to give good accuracy. The accuracy will drop. So such kind of mechanism is an overfitting mechanism where it is fitting good on the training data but not on the testing data. So to avoid overfitting, we have to introduce such kind of break, which means we are not allowing our model to learn everything from the previous layers. We are allowing some kind of break. So if we are providing some breaks and if we are not allowing each and every neuron to connect with each another other neuron, so model will now start doing assumptions. What is assumption? Model will try to generalize the data. When the model generalize the data, here the model becomes more intelligent and gives the decision based on newer approach or some generalized approach. So model becomes good in generalization. So it is like there are two types of student. One student who studies everything and answers everything, but when we give him a new test with new set of questions, he is not able to answer. And there is a student who is not learning everything, he is learning partially, but he is trying to solve problems, newer problems which are not at all there, or he is very much exposed to new environment. So such learner will be able to work well or perform well in both the situation when he knows the question and when he doesn't know the question. So he will equally be able to face such kind of questions. So that is why to reduce overfitting we are using this dropout mechanism of our data. So when we do it, we drop out the data here between these two dense layers, which means here the first layer is fully connected, second layer is partially connected, and in the softmax or the last layer we are using y dot n unique. Now what is this y dot n unique? Y dot n unique is the total number of categories in the y column. Okay, so what is the y column? That is our output. So in the output, how many total number of unique categories are there? So there are y dot n unique. So we saw it was 5. So at the output layer we will have 5 neurons. Okay, where it will be these neurons will be created with the help of softmax function, which means these 5 neurons are created using softmax function. Now what happens in a softmax function? There is probability assigned to each one of those, and when we sum up the probability it is going to be 1, which means the value or the category which has highest probability will be considered as the category this particular category, suppose this category has the highest probability among all other categories, so that is the class of that particular input row. So based on that, the softmax activation function works. And then we can also use checkpoint, model.checkpoint. So sometimes it is not working in the newer version, so you have to downgrade your TensorFlow and then work on it. So better you can use it, otherwise you can skip it out. There will be you can refer to the Keras documentation, official documentation for model checkpoints and callbacks process. So what is callbacks process? Now when I am developing a model, as I discussed, like there was a point in the regression part where where we saw that at certain points the loss is going down, again the loss was increasing. So say epoch number 5, so loss is 22, and epoch number 6, the loss is 27. So I want low loss, I want minimum loss, so I want to preserve the weights of epoch number 5. So how we will do when we are working on a data set which has multiple epochs and multiple data values? So for that we will use this model checkpoint approach. So what happens in model checkpoint? In model checkpoint, it will run across each and every epoch, and it will store whenever the model loss is going down. So for example, here the model loss was 25, error loss was 25, and here the error loss is 22. So it will store this error loss, the weights corresponding to this epoch. So whatever was the weight for this epoch, it will get stored in this stored in the callback, and accordingly all the places wherever we are getting lesser error, all those will get stored as a callback, and we can use it for developing a model. So I'll show you how it works actually. So first part is model checkpoint. Model checkpoint we have imported. So model checkpoint is to create a checkpoint wherever we are having less error. Okay. So the first thing is we will compile the data. While compiling, we are using optimizer, which is Adam. Now we are using loss as sparse categorical cross entropy. Sparse categorical cross entropy is used whenever we have classification data set. So here we are doing classification data set. So we will have sparse categorical cross entropy. If it is regression, we are using mean absolute error or mean squared error. So our loss is sparse categorical cross entropy. And matrix, we are keeping accuracy. We are focused on improving the accuracy of this model. So our objective is to find higher accuracy in a model. And then we are using checkpoint. So checkpoint will do what? Checkpoint will we will create a model checkpoint, and in this model checkpoint we are going to create a checkpoint using model checkpoint, and the checkpoint name will be this. So the name is best model weights. It is getting stored into my working directory. So when I run it, it will get stored into my working directory as best model weights.h5. So this is a file which will get stored, and this file stores the best weights out of all the epochs that we have run. We are going to monitor validation accuracy. So we are monitoring validation accuracy because validation is a newer data set on which the model is getting fitted. Then we are using SIF best only as true, so which means that it will run across all the epochs one by one, and it will save the best weights as best model weights.h5, not all the weights. And it will we are using mode is equal to maximum, which means maximum accuracy we are trying to fetch. So let's try to understand the implementation part. So when we use history, when we run the model, we will fit the data as X-train and Y-train. We are keeping a batch size of 100. We are keeping epochs as 100, and validation data we are putting as X-test and Y-test, and callbacks we are putting as checkpoint. So here we are using an argument called as callbacks, which we have not used in the regression. So we can use it in regression as well. So when we use callbacks is equal to checkpoint, so it will call this checkpoint, and it will use this model checkpoint, all these parameters. So these are the settings. So now when my model starts learning, so epoch by epoch it will start learning. So let me show the entire epoch by epoch arrangement. So in the first epoch, the model fits the data X-train and Y-train, and model validates on the X-test and Y-test. So here I am providing my validation set also. So training will happen on X train and Y train, and it will check if it is making correct predictions or not. So in the validation data set, if in the epoch number 1 the accuracy is 0.09, which is very low, and the loss is 1.8640, which is very low, and that is why we can see it is the loss is 1.582 on the data set. Accuracy is considerably increased here, the accuracy is higher here, and the validation loss is 1.3 and validation accuracy is 0.39 in the first epoch. So we will focus on validation accuracy for now, and let's see how it is getting improved over the time, because here we are going to monitor validation accuracy. Wherever we are having validation accuracy as high, we are going to store that weights, corresponding weights. So that is why we will focus only on validation accuracy epoch by epoch. So if we talk about this epoch, validation accuracy is 0.39, and epoch number 2 we can see the validation accuracy is 0.37. okay, we'll move forward. In the epoch 3 the validation epoch is accuracy is 0.47. now what is happening? So here accuracy was high, the weights corresponding to this accuracy will get stored into this checkpoint. Now in the second accuracy, second it is getting down. So in the second epoch the accuracy is low, which means we are not going to preserve the weights for the epoch number 2. In the third epoch the accuracy is increasing, which means now we have to replace the weights which were earlier preserved. So we will replace the weights which were earlier preserved, and we will store only the weight of epoch number 3. Similarly, in the fifth epoch, we are seeing a considerable fourth epoch. We are seeing a considerable improvement. We are seeing the accuracy, validation accuracy going up as 0.54, and we will store that epoch weights now. We will not store the weights for third epoch. Similarly, when we go for fifth epoch, the accuracy increases. Now, the old weights will get replaced, and we will store the new weights of epoch number 5. And similarly, as we go down and down and down, it will keep on replacing whenever the accuracy is increasing. If the accuracy is going down, it will not replace, it will preserve the old weights only. So this is how the process goes. Like here, if you see the epoch number, let me confirm, epoch number 10. So in epoch number 10 the accuracy is 0.95, but in epoch number 11 we can see the accuracy is 0.93. So which means here the weights were fine, it was working fine and showing high accuracy, but here the weights got down. So here the accuracy is got down, so we will not save the weights of epoch number 11. We have saved only the epoch number 10 weights. Now we will move forward in epoch number 12. Epoch number 12, again 9571 is our 9571 is the accuracy here. Earlier we had 9500, so which means epoch number 12 is better than epoch number 10. That's why the weights of 10 will be removed and the weights of 12 will be preserved. This keeps on happening continuously at the end, which means once the entire epochs are finished, like 100 epochs are done, wherever we see highest accuracy, here in this the highest accuracy is at epoch number 97, where the accuracy is 100, which is 1.0, which is 100 completely accurate model, which is considered to be. So the epoch corresponding to so the accuracy corresponding to epoch number 97, or the weights corresponding to the epoch number 97 is now added to the callback. And now we will do a simple prediction here. So when we do the prediction, and we have created the model, the weights have been saved, we will do the prediction and we will see that some value is getting generated. So when we talk about ypred, so ypred we are putting all x data and we are predicting the prediction. So these are the values generated, 0, 1, 2, 3, 4 categories or classes, and we will see how the model is performing over the testing data, and we can see that model has perfectly performing over the testing data. Only one problem is there in this particular, when it is trying to predict say category number 4 or 3. So here we are getting error, otherwise the model is perfectly working on the testing data, which means here we have developed a perfect model. Ideally it should not be, because as our model is very as well we are training, we are getting a good model, but Ideally, as the way we have arranged the data, it was not logical at all, so it should not be relied upon. But yeah, this is how the model works. And now we will predict the history of the data. So history, how the model accuracy or validation accuracy compared to the original model accuracy were. So we can see that as the model accuracy was going down, which is in red color, the accuracy of the validation was also going down, which is in green color. So red color and green color both are going down in a similar pattern, which means the training accuracy and the testing accuracy, or training loss and testing loss, are going down in a same fashion, which means they are totally aligned, which means the model is learning well on training as well as validation, both the methods. And same we can see for accuracy as well. So model is learning well over training as well as testing. We can confirm it with respect to accuracy, this graph. Okay. Now if you talk about this weights, we can use this weight which we have preserved, which is stored in the form of H5 format, best model weights.h5. So we can call in any time, and we can create a model out of it, and that model can be utilized for building accurate models. Okay, so right now we are saved with highest accurate model, and that's what we are getting. We are getting a model which is highly accurate. Somewhere we can see a little bit reduction, but yeah, the accuracy of training as well as testing are totally similar. So we have developed a very correct model here. That's the implementation of classification algorithm. How we can implement a classification: we have to do the same data cleaning process as we are doing. You can use your own strategy of cleaning the data that you have done. This is entirely focused on deep learning classification. You can clean the data as per your data cleaning methods, encoding methods, decoding methods, missing value treatment, outlier treatment. Further to that, you can use standard scaler. After that, you can just use the train test split, and you can call in the sequential model, and you can add up multiple layers, that is dense dropout, compile the model and fit the model using training and testing data with the epochs that you decide, and this way the model will learn accurately from the data.